How are you, Ahmed?
Oh yeah, I have a mic now. I found the mic. So yeah.
Okay, no problem. It's okay. So let's give this a.
Good morning. Let's learn about rolling without slipping.
Flippin' physics.
This is an object which is rolling without slipping. Now,
We are talking about rolling without slipping, guys. Rolling motion. And rolling motion is not rotational motion only. It's rotational and linear motion, both of them combined together. And let's see that this voice is too loud.
it might seem obvious, however, realize there is no slipping which occurs at the contact point between the object which is rolling without slipping and the surface it is rolling on.
Yeah, that's what it is.
Rolling without slipping, that's what it means.
Right, so again, rolling without slipping. I'm going to isolate 2 points on the object which is rolling without slipping. The center of mass of the object is a dot in orange and a...
This is center of the mass, and this point on the edge of the rolling object. Again, this object is rolling without slipping on this surface. We check 2 points. This point in the middle, center of the mass, and this point on the edge. We will choose these points, 2 points, to see what are the velocities of these 2 points in rolling motion.
A point on the edge of the object is a dot in blue. I have also added dots which track the locations of those points. You should be able to see that the orange dot at the center of mass of the object rolling without slipping is moving at roughly a constant velocity.
You see these dots here represent the velocity, represent the speed. And this, because we have distances between these dots is equal, or they show a regular motion here, this is a constant velocity. It's in the same direction. It doesn't say it changes direction. So it is at the same height from the table here. So it moves in a straight line with a constant speed in the same direction. So we call it constant velocity. This is for the point in the middle. But if we look at the blue point, you will find that it moves in a circle or have a wave motion like this one. It doesn't have a constant velocity or constant speed. Sometimes when it comes to contact here with the table, it comes to be 0. Because if it has a velocity when the contact is with the table surface, it will slip over the table. And there is no slipping. This means when this point, the blue point, touches the table, it will have a velocity equal to 0. A velocity equal to what? 0. So we have a constant velocity for the center of the mass, the point in the middle. And the blue point here has a variety of velocities or a changeable velocity. When it touches the table, it will be 0 because the table is stationary. So when it touches it to a stationary object, it must be stationary too. When it moves away, the velocity increases to reach the maximum at the highest point here. Let's see how we how can we calculate the velocities of the blue point at different parts of the motion or different locations of the motion.
The dot in blue, which is at the edge of the object rolling without slipping, traces a more complicated pattern.
Oh, that's a cycloid. A cycloid is a curve traced by a point on a circle which is rolling along a straight line.
Absolutely.
This motion, we call it a cycloid. When it has different of velocities, a curve traced, this is the curve, we call it cycloid, by a point on a circle rolling in a straight line. So this cylinder is circling on a straight line without slipping. It will produce a cycloid. This blue curve, what you see, it is called cycloid.
Absolutely, Billy. The blue dot is tracing out a cycloid.
I actually think that looks pretty cool.
Yeah, totally.
Sure.
Believe it or not, I agree. Okay, rolling without slipping is actually a combination of 2 types of motion. It combines pure translational motion.
So again, rolling motion, combined rotational motion because it's rolling, it rotates, and transitional motion, it moves in a straight direction, in one direction. So rolling motion has both of them.
With pure rotational motion.
So he combined them together. This is rotational, revolving, rotation, rotating around the axis of rotation, and the rotational motion and transitional motion. It moves in a straight line. They will be combined here in rolling.
As you can see, every part of the object in pure translational motion has the same velocity to the right.
So if we have the same object is moving without rolling, without rotation, all particles will have the same velocity. Okay? Here in the rotational motion, we can find the velocity depending on the relation V equal omega r. Okay, but here in this one, we have both of them in one object, ruling. How we can find the velocity for different parts in this ruling object? Let's see.
Therefore, every part of the pure translational motion object has a velocity equal to the velocity of the center of mass of the object. This is not true of the pure rotational motion object. The center of mass of the pure rotational motion object is not moving and therefore has a velocity of 0.
Here, in the rotational motion, the velocity of this object, I mean linear velocity, is 0 because it's not moving anywhere. But this point has a velocity of v equal omega r. So the velocity will gradually increases once you move away from the center of rotation or axis of rotation. So that's what happened in rotational motion. Again, in translational motion, all points move with the same tangential velocity, which is equal v. And here, this point, we have the center of the mass or the center of rotation has a velocity of 0. The point on the edge will have a velocity v equal omega r. The point in the middle will have v equal omega r. So the velocity, linear velocity, will vary when we move away from the center of the rotation. It starts from 0 until it reaches equal v equal omega r at the edge.
However, the outside edge of the pure rotational motion object has a tangential velocity equal to the radius of the object times the...
So that's it, v equal omega r. The radius multiply the omega is the rotational velocity or angular velocity.
the angular velocity of the object.
You see this one? That's it.
When you add those together on the object, which is rolling without slipping,
So we will add this motion with this motion to have ruling motion. We will add both of them to have ruling motion. Let's see.
you can see the top of the object has a velocity equal to the velocity of the center of mass of the pure
So we are combining, focus here, we're combining rotational with transitional in ruling. We will combine the pink arrow with the blue arrow here in ruling. So this arrow is always moving in changeable direction. The blue arrow all the time points toward the right, as you see. So we will combine the blue arrow from the transitional motion here with the pink arrow here. So we will have double of the speed, which would be v equal 2 multiply omega r. Let's see that.
translational object plus the velocity
That's it. One come from rotational motion at this point, and one come from transition. Transition all the time is constant. V equal omega r, this one. And this comes from the rotational motion. So the velocity here will be the double.
of the edge of the pure rotational object, which is radius times angular velocity. Both of those velocities are to the right. The velocity of the center of mass of the object, which is rolling without slipping, equals just the velocity of the center of mass of the pure translational object, because
The center of the mass will have only half of this, have only the blue arrow, which represents that transitional motion. There is no ruling for this one. It's only transitional motion. So it will have only the blue arrow, which represents that transitional motion. While the point on the edge will have two velocities, one from ruling, one from rotation, and one from transitional motion.
because the velocity of the center of mass of the pure rotational object equals 0. The velocity of the bottom of the object, which is rolling without slipping, is the velocity of the center of mass of the...
Now, let's take the bottom. This is the arrow for the bottom at this point, represents the velocity. And the blue arrow represents the transitional motion, according ruling. Both of them will be in opposite direction. The point here, when you come to the point, the blue arrow will cancel the pink arrow. You will have a 0 velocity. In the same time happens during ruling. So the point at the point at the top will have double of the velocity, v equal 2 omega r. This one will have all the time only v equal omega r, and this point will have a 0 velocity because the ruling rotational motion will cancel out the transitional motion and will have a 0 velocity.
Pure translation of the edge of the pure rotational object, which is radius times angular velocity. Going back to the cycloid for a moment, do you all see how the very bottom of the object rolling without slipping actually does not move relative to the surface? And
this point is not moving. It has a 0 velocity in the cycloid motion.
Therefore has a velocity at that brief moment of contact, which is equal to 0?
Okay, sure.
Absolutely.
So this point will all the time have 0 because if it has a speed, it will slip. No slipping, so the bottom speed equal to what? 0. I'm not talking about the speed of the whole object. I'm talking about the speed of this point when it comes in contact with the table. It will have a 0 meter per second speed, because again, if this point has a speed, it will slip over the table. Okay, guys? When it touches the table, it will have the same speed as the table, which is 0 velocity or 0 meter per second.
It is not slipping, so it is static friction. So the velocity of the bottom of the edge of the object rolling without slipping has to equal 0.
Right, that means the velocity of the center of mass of pure translational motion minus radius times angular velocity equals 0, which means the velocity of the center of mass of pure translational motion.
So he deduced here that the center mass, velocity of the center of the mass, must be equal r omega. This is how we conclude it here. Okay, guys? So the transitional motion has a velocity of r omega for the center of the mass only. If we come to the point on the top here, it will be double of that, which it would be r omega from transitional motion and r omega from the rotational motion. It will be double. The point here will have 0. Let's see that.
Equals the radius of the object.
Remember, because it is
To the equation.
equals the velocity of a point on
That's
the
it. You see this part? We'll start here to see the combination of them. Let's see that.
Let's take a moment to look at the velocity of a
This black arrow represents the sum of them. When at the top, it will be the double. You move down, you start to decrease the amount of summation or sum of the two vectors until it will become 0 at the bottom. Let's continue.
point on the edge of the object rolling without slipping. Remember, it is the addition of the velocity of the pure.
So all what I'm explaining here is called ruling motion. Ruling motion. Again, let's come back to our slide here. If you see this, we have here center of the mass has a speed of what? R omega, only R omega. While this point on the top has a speed of equal what? 2 multiply R omega. I've explained that. I wish you understand it. So that's it. The bottom here, if you see that, the bottom has the velocity of what? 0, because no slipping. So that would be a static friction. I think that explained that before when we talk about static friction. When you walk, when the car is rolling, it has a static friction because there is no sliding. Static means this point of the wheel is not sliding over the road. So this means it has the same speed of road. Road has 0 speed, so the speed of the cycle or the wheel here has 0 velocity. And on the top here, we will have a speed of double of r omega because we are rolling, no rotation. And the speed of the center of the mass, the middle of the axis rotation here, has a speed of r omega only. In the middle here, it will be between, it will be less than, the velocity here will be greater than r omega and less than double r omega. Let me read that. And less than double r omega. And the last question for those smart of you, smart students, inshallah تجاوبوا يعني. This is speed between these 2 points, between this point and this point. Which means exactly this dots in black. This dots in black, it will have a speed ranging between r omega and double r omega on the top. Here double r omega and here r omega only. The question here, what is the speed is ranging here between this point and this point? And let me make it in blue. So what is the speed ranges here in these blue dots? The speed ranges between what and what? I'll make it in blue. V is greater than what and less than what? Who can answer me? يا قوم.
I honestly don't know.
Okay, I want someone to know.
RW and 0.
Huh? Yes, greater than what?
RW and 0.
No, what I have to put here?
Greater than 0
Greater-
and less than
Greater
RW.
than 0. Bravo, bravo عليك. Yes. And less than R omega. Yes, it's omega, not W. Bravo, Muhammad. Yes, that's it. Muhammad was focusing with me. So I said the velocity here of the edge here ranges in the cycloid. The top will have a double R omega. The bottom is 0 and ranging between that. And the middle is R omega. So from here to here in the black dots, it's ranging between R omega and that is this point and double R omega in the top. And here in the bottom, it will range between 0 on the bottom, V will be greater than 0 from this one, and less than R omega. Okay, guys? So we have, if we follow the point here on the edge, it will follow a cycloid, while the point here will follow a constant velocity. Physics, guys, you have to understand this. So let's continue. We have explained what does it mean, the rolling motion, and we have explained the cycloid motion of the edge of rolling motion. And we have said that rolling motion is a combination between rotational motion and linear motion. That's it. I think that you can see it right now. The rolling motion of a wheel is the combination of both rotational motion and linear motion. I think that you have understand this right now. Let me pick someone else to read. Ahmed Al-Mulla. Ahmed. Are you with us, Ahmed? Ahmed. Yeah, Ahmed. Ahmed Tawfiq absent. Ahmed Anwar absent. Ahmed كان حاضر معنا من شوي.
هلا أستاذ، أنا موجود. موجود.
Where have you been, Ahmed? I have called you for.
والله ما أدري، فكرت كنت تنادي أحمد مشعل، لأن أنا صوتي شوي قليل على شو اسمه، على اللابتوب، يعني ماني مطول الصوت. فيا.
Okay, I want you to read this slide. Let me bring it to you. Okay, this.
Okay.
What is? No, not this one. This one.
Okay. Because rolling motion and the moment of inertia. Because the forward motion of the axle exactly cancels out the backward motion of the bottom of the wheel, the instantaneous speed of the bottom of the wheel is 0. The top of the wheel has twice the speed of the axle. Thus, if a car's speed is v, as read on the speedometer, then the tops of its wheels have the speed 2v.
This is very important thing that you have to understand it. The car, you have in rolling motion, you have wheels rolling on the road. The speedometers will read which speed. We have ranging speed. If we go back here, where is it? Yes, here. I told you we have ranging speed from 2r omega until 0. The speedometer reads the speed of the axis of rotation, which is r omega. You understand this, guys? So if you're moving with 100 kilometers per hour, only 100. The speedometer reads. What does it mean? What this speed is? Kilometer per hour. This is the speed of the center of the mass, axis of rotation. Okay, guys? So this is 100. What about the speed of the top of the wheel? It will be what? If the speedometer reads 100, the top of the wheel will be what, guys? حد يقول لي قبل ما اكتب انا؟ What would be the speed of the wheel, guys, on the top? Again, speedometer reads the center of the mass or the axis of rotation speed, which are omega. If it's 100 kilometers, what would be the speed of the top here? Top ده يبقى كام? Someone open the mic and tell me. ما شاء الله. حلو السكوت ده. Guys, anybody knows what is the answer for this question? If the speedometer of the car reads 100, I tell you that the speedometer reads the velocity of axis of rotation, which is VR, R omega, V equal R omega. So R omega equal this number. I give you example. If the speedometer reads 100, what would be the speed of the top of the wheel in this time, at this point? I'll pick someone.
200.
Yes, it's 200. It's not difficult. R omega, double R omega. It's 100. This one will be double R omega, 200 kilometers per hour. So if you're moving with 200, velocity 200, you are reckless boy, and moving with high speed 200 here, this will be 400. And this, you can imagine the tire, the pressure the tire is upon in this time. So let's go back to the slide here. The top of the wheel has twice the speed of that. If the car speed is v, as read on the speedometer, then the top of the wheel will be 2v, because the speedometer reads the velocity of the axis of rotation or center of the mass of the wheel. It reads the speed of the center of the mass. Let me pick someone else to continue read with us. What's this one? Hassan? Yeah, Hassan. Hassan.
Yes, Mr.
Why you take so? I'm really not Hassan only, but all of you grade 12. When I call someone, he answer me after a while. This never happened with any other grades. Why? Tell me a reason for that.
No, I was bringing something.
He was bringing something. Okay.
Yes.
Okay, Hassan. I want you to read this slide, Hassan, please.
Okay. Due to its inertia, an object at rest or moving in a straight line resists changes to that motion. A similar relationship occurs with rotational motion.
Hassan.
Yes.
Step slowly, واحدة واحدة حبيبي. Slowly, take your time.
Okay. I reread it يعني ولا I start slowly from the next paragraph?
From the first paragraph.
Okay. Due to its inertia, an object at rest or moving in a straight line resists changes to that motion. A similar relationship occurs with rotational motion. Each object has a moment of inertia, which determines how easy or hard it is to change its rotation. An object with a large moment of inertia is difficult to start or stop rotating. For example, a merry-go-round has a large moment of inertia, whereas a baseball has a relatively small moment of inertia.
So he's introducing us this line for rotational inertia, which we talk about it previously, or moment of inertia. So the moment of inertia, generally it's called rotational inertia. I said in the linear inertia is equivalent to or can be measured by the mass. If we have a larger mass, we will have a larger linear inertia. Here in moment of inertia, there are two factors. We have explained that affect the moment of inertia. They are the mass and the distance from the center of rotation. I have explained that before. I will just read it with you. The mass that's rotating and the distance from the center of rotation squared. So we can say that the moment of inertia mainly depends on the distance from the axis of rotation. If we increase distance, if we double distance, we will increase the moment of inertia or rotational inertia 4 times. While if we double mass, we will double only the moment of inertia. So the great effects belongs to the distance from the axis of rotation. If you increase the distance, you will increase inertia and also mass, but mass, the effect of mass is not like the effect of the distance from axis of rotation. So let me pick someone to read that. Karim?
Yep.
Read this slide.
Experiments show that an object's moment of inertia depends linearly on the mass of the object and on the square of the distance to the object from the axis of rotation. For a mass m at a distance r from the axis of rotation, the moment of inertia is I equal mr squared, or mass times radius squared.
Thank you. And don't forget, what are the units of inertia or rotational inertia? Mass kilogram and r square meter square. So the units of moment of inertia kilogram dot meter square. Kilogram dot meter square. This relation, where would you get from? Not from deduction, it's from experiment. In the beginning, we got this relation between moment of inertia. How to calculate it? It comes from experiments. And this one explained it also yesterday. If we have more than 1 point mass, we will find the moment inertia for all of them by adding them together. We also explained that yesterday, but let me see someone. Khalid Joyman, I think is not here. Kumail. Kumail? Kumail.
Yes, hello, mister.
Hello, Kumail. Okay. I want you to read, sorry, this slide. Yes.
This one, rolling motion and the momentum of inertia.
Moment of inertia, yes.
Okay. In a system with several particles with different masses and at different distances from the axis of rotation, the moment of inertia is the sum of the mr squared terms for each object.
So that's it. If you have more than 1 point mass, we have explained that yesterday. I don't know if we take it here or not. I don't think that we typed it here. But if we have more than one object that is rotating, I can do that for you in a new slide. Alhamdulillah. So that's a slide, and we have here, sorry, this is, and we will have an object here. That is rotating, one object here, mass 1, in this point, and another mass will be Control C, Control V, Control V. We have two other masses, one here and one there. So that would be, if you remember that, we talked about this yesterday, this is M1, and this is R1. And that is M2, and that is R2 from the center of rotation. Okay, and that is M3, and this is R3. This is M3, and this is R3. To find the moment of inertia or rotational inertia for this system, and this system is revolving in this direction, for example, you will type it like this: moment of inertia equal M1 R1 squared plus M2 R2 squared plus, and you can continue like this. We are considering M1 and M2 and M3 as point masses. This means we consider all points over the M1 at the same distance away from the center of rotation. This is the meaning of point mass. And this happens when we have a very large R comparing with the dimensions of the M itself, whatever. So we will combine all the inertia, moment of inertia or rotational inertia for each point individually, and we will add them together as you see. Okay, that's it. This is for a system, and that's what was Kumail reading in this slide. We find the moment of inertia. And the total moment of inertia, we add them together. It has a units of kilogram dot meter square. It's the same units for every, if you have only one. So this one, we talked about it yesterday. Let me pick someone to read it. Mishal. Mishal. Absent. Muhammad Fahd Boudi.
No, I'm present, Mr.
Okay. Mashal, I want you to answer this question, to read this slide. Read this.
All right. Which line?
Slide. This one, all the.
Okay. The preceding results are valid for individual particles or groups of particles. What about a solid object, like a disk or sphere? The table below contains the moment of inertia for several uniform rigid objects of various shapes and total mass.
So here we are describing different rotational inertia for different objects. Okay, guys? The preceding results are valid for individual particles or point masses, as I told you, or groups of particles, group of point masses. What about كلمة particle? The word particle means point mass. What about a solid object like a disk or a sphere? How can we find the moment of inertia for this object? So that's how we can find it. This table shows us how to find it. And this table, we take it yesterday. That's it. If you have a ring like this one, the moment of inertia equal mr squared. Exactly like what? Exactly like a point mass. Okay. The M is the mass, the whole mass of the whole cylinder, the mass of this cylinder. If we have a disk or solid cylinder, okay, not cylinder shell, a disk or solid cylinder like this one, the moment of inertia will equal half mr square. This is how to calculate it. And this is the center of rotation is in the middle. The axis of rotation is in the middle. If we have a solid cylinder and the axis is tangent to the edge, it will be 3/2 mr square, and so on. For each shape, you will have a different moment of inertia. The higher the moment of inertia, this is mean it's difficult to make it rotates. So I'm going to ask some questions here for those who are with us. I'll ask the question generally. Who want to answer it, answer it. If nobody answer it, I will pick some. Yes.
I'm sorry for interrupting, but Ahmed al-Mishal says that he's talking, but you can't hear him in the chat.
No problem. I want to ask question. Which one will be easier to rotate? And this question is general for any one of you. To rotate a cylinder shell or a solid cylinder, which one is easier to rotate? Let me give you a question in other form. Let me give the question in other form so you can understand it. Let me do that for you. تستاهلون انتوا هذه الأسئلة والله. Okay. Let me draw this for you. And I will flip it. So sorry. I'll flip it like this. I want it like that. Okay, we can't flip it, no problem. Let's leave it as it is. And I will put here two cylinders, two things. One of them will be a sphere shell that's going to rotate here. Okay. Control C, Control V. So I'm going to put this both things, and this one will be will not be a shell, it will be a solid cylinder. And I want you to think, لو انتم مركزين. The question says, which one of these will reach the bottom first? Are they going to reach the bottom at the same time, or one? But the way this is a shell, this is shell, and this is solid. This is shell, and that is solid. How many time we have for the time right now? We have only 1 minute. Who can answer this question? We will start with it. Anybody can answer it?
We only can try. 1 minute.
I'll give you this. We have only 1 minute. If you can do it right now. Again, you will use hint. You will use this information here.
The solid one?
And solid one, why? Why you say the solid one? Try to explain using this information.
Because it has low inertial momentum.
Bravo, low inertial momentum. And if you have low rotational momentum, what does it mean?
You have higher acceleration.
Yes, it's easy to rotate. So if we come here, the solid one is easy to rotate because it has low moment of inertia. Okay? So it will be easy to rotate, so it will rotate faster. So it will reach faster. هنشوف الكلام ده ان شاء الله الحصه اللي جايه عملي في فيديو. Thank you guys. See you after the break.